In this video, we'll continue moving through section 4.5 and we'll get more practice with U substitutions in general. The previous video, we got the basic idea. The idea of when we're in some trouble, when we have problems with multiplication, division, or inner outer, we pick U as the inner function. But now, before I start giving you more examples, what I would like to do is go back to an old f prime chart. And as I noted back in section 4.4, now that we've finished all the formal notation, the book gives you a whole new list of integral rules. Things like the integral of cosine is sine. And as we've mentioned in these videos before, I think that is a big mistake. I think that we should really get used to derivatives and antiderivatives as close together as we can. Don't memorize separate rules because we keep seeing how similar the rules are. So now you'll finally start to see why I've always used U as a letter when we make this chart. Because now when we make U substitutions, we're going to look for things like this. So in the previous video, we ended up with U to the n power du. We made a U substitution, and after we cleaned up, we got something like this. And we know that is its correct antiderivative. We had that exact same thing for x to the n, but now I'm including the du. So again, when we make U substitutions and we talk about, is our integral good? After we've substituted and simplified, is this a good integral? It's really going to be, is that something that now fits the right side of our chart? And 2 out of our 3 problems ended up with this. We had a U to the 5th and ended up with 1/6 U to the 6th. We had a U to the 1/2, so we had U to the 3/2 with a 1/3. So we've already used that idea twice. And now for the trig functions. I'm going to do it from the derivatives. The derivative of sine U is cosine U du. But notice we use that one as well. In the third one we did in the last video, we had cosine of x cubed plus 1. That became cosine of U du, and the anti was sine of U. So I really think by making these U's, we could use this for derivatives and antiderivatives, and this is a very helpful chart, both for finishing Calc 1 and for those of you moving into Calc 2. I will say, when I teach Calc 2, I point out we start with this chart with 7 functions on it, and when you finish Calc 2, you've got like 22 functions on it. So Calc 2, you got to know this in the first place, but you really increase it a lot. But again, that's Calc 2. Let's stick with Calc 1. So the derivative of cosine U is negative sine U du. The derivative of tan U is secant squared U du. The derivative of cotangent U is negative cosecant squared U du. For secant U, we get secant U tan U du. And last, cosecant U, we get negative cosecant U cotan U du. I hope you already see how we use the U substitution for this one in the last problem. But as we get into some of the other trigs, these things still look ugly. You still have multiplication. You still have inner outer. But if that's the big picture with antiderivatives, do you know something that has that as a derivative? So if we can make a U sub to get something that looks like this, that is a good U sub, and we can then take the antiderivative. So I'll keep coming back to and referring to this chart, but now let's start doing some more problems. So let's evaluate. For the next bunch, everybody, I'm almost entirely going to stick with just indefinite integrals. We'll do one more definite integral. But we saw in the previous, even if it's definite, you'd still do a U sub in the same way. It's just a little option at the end to back sub and then plug in your original x's, or to push the limits to get new U values that would go as our bounds. So let's evaluate. And let's actually start a little simple. You know, the last video, we already looked at something a little complicated. Let's start a little simple here. Let's evaluate, number 1, let's look at the integral of sine 5 theta d theta. I mean, this is not that bad. And this has a little bit of an inner-outer issue, but it's minor enough that I will be honest, some people can just force their way through this. How can you take a derivative and get sine? You must have started with a negative cosine. Because positive cosine is derivative negative sine, so negative cosine would have negative negative sine, positive sine. Well, angles don't change. So this must have had an inner part, an angle 5 theta. So that cosine 5 theta gets me a derivative sine 5 theta. But this would have a derivative with an extra times 5, so needs to be balanced with a 1/5. I did not use a u sub, and that's what I was talking about in the previous video. Some people can just kind of fight their way through it. Seeing enough pieces to keep working, well, I must have had a cosine, and then that gives me the extra negative. This angle must match, and then it's about getting this to be the magic number that makes everything perfect. So that works, but for a lot of us, it's just easier to say, hey, inner, outer, let me pick u as my inner. Well, then the derivative of u would just be 5 d theta. And again, the book's way, they'd say, hey, you've got a d theta, but you need a 5. So I do a 5 1/5. But for us, just divide that by 5. This becomes sine of u, and the d theta becomes a du over 5. There's a 1/5. We won't always, these numbers won't always end up in the denominator, but this one does. So an extra 1/5 out in front, and the anti of sine u is negative cosine u. So they would get here negative 1/5 cosine u plus c, and then they just simply back sum. Now this one, it's not just because this was a trig function, it just really was just the inner outer. The inner was just barely more than just a theta or just an x. Okay, so now let's do number 2. And let's take a look at another, again, not easy, but nothing too crazy either. Let's look at the integral of 4 minus 3t to the 10th power dt. And again, now I switch to variable t, just so again, we're not always stuck with x's. That doesn't make a difference. And again, just as I showed you here, some people can fight through this enough that they can just do some good reasoning. I'm showing you this first, everybody, but I gotta be honest, I do not think this is the better way for most people to solve. So I'm showing you this quickly, but I really want to concentrate on the u idea. Here we went through the u fairly quick because these both matched pretty fast. This one I think is a little bit harder, but some people can still fight their way through it. How do you end up with 4 minus 310 to the 10th? Well, you must have had a 4 minus 3t to the 11th. Well, that would need a 1 over 11 out in front. But this would have a derivative with an extra times negative 3, so this needs to be balanced with an extra divide by negative 3, or times negative 1/3, and a plus c. And I could clean that up a little bit, but again, I even intentionally am trying to show you that's not easy. And there's a lot of like, well, this has to and could, but it's not a set in stone idea. So while this is correct, I'm going to cross it off, scribble it out of the way, and let's do it using a u substitution. So even though this one is not that bad, it still has inner outer. It doesn't have any extra multiplication or division, but it still has inner outer. So let's pick u as the inner. So the derivative of u, just be careful here, 0 minus 3. So I'll get a derivative of minus 3, and that'll get marked dt. Notice, everybody, if you are not substituting over here, if you're just miraculously becoming u to the 10th and just changing that into a du, sometimes things won't cancel properly, or other times, like this one, your answer will just be a little bit off, and it could be frustrating, and you don't know what's wrong. So you need to, again, solve this for dt. So I'll divide the negative 3 over. My new integral It's still an integral. I'm still not taking the antiderivative. That's another, I know I'm pointing out a lot of common mistakes as we go through this. There's a lot to get used to here, but to realize I want to embrace the notation. The u substitution does not take the antiderivative for you. It's just trying to simplify the problem so you can take the antiderivative with our more traditional techniques. So still keep my antiderivative, and yep, now this is u to the 10th, but now I get a du divided by -3. So that is a -1/3 out in front, u to the 10th du, -1/3, 1/11th, u to the 11 plus z. It's a new technique, but notice, just like we've always said, the integral sign drops when you take the antiderivative. The du or the dx drops when you take the antiderivative. That's when something comes up at the end. A definite integral will get the bar. The indefinite integral gets the plus c. And now when I back sub, just notice I'll clean this up a little bit. The -1/3 times -1/11 would give me a -1/33. But then the u to the 11th becomes 4 minus 3t to the 11th plus c. And that matches what we said before. But this would be the more common technique for everyone to follow. Okay, so let's keep going, everybody. Still want to do a couple more. Next, let's look at the integral. Let's look at 4x plus 4 over the quantity x squared plus 2x plus 5 cubed. And which one? This was number 3. Still evaluating. Oh, and this is page 4. Now, this looks a bit messier, but again, still not that awful. I've got division. May not look quite like it, but number 3 is very similar to the original one that we started with. I've got inner outer, and I've got this ugly multiplication issue. And again, I couldn't practically clean it up here. I couldn't clean it up at all right here. In this one, I've got this division. There's no dividing this, and I've got this inner outer. So it still works. It still is giving me an ugly situation, but I'll let u be the inner piece. So that'll be the x squared plus 2x plus 5. All that would be the inner. Du, the derivative of that inner. Technically, this is 2x dx plus 2 dx. But most people just write the dx once at the end. And some people even have a bad habit of just leaving that. We should be clear, that's all times dx. And that's especially important because in the previous, your u's after you took the derivative were easy enough that it should have been a little obvious that we needed to divide the 3x squared to isolate the dx. But here, without the parentheses, now people start subtracting 2x, then dividing by 2. But it's all divide the whole thing over to isolate the dx. Now, the more people get accustomed to doing this, again, I don't want to jump ahead, but for those going into Calc 2, you will do this often enough that when you have problems like this, you'll already have a good feeling right here that this is working. Because you know the x squared was the extra piece of x, and that was going to need something to cancel with it. So seeing the x squared, the extra 3 was fine, but seeing the x squared was huge to realize that would eventually help me cancel. So some people can already start to envision that we're going to need this to help cancel with this. But for plenty of us, again, we're still not at that stage. It's after we get a little further we start to notice those things, and that's what's going to happen. But initially, well, the 4x plus 4 is hanging out. This became a u to the 3rd power. The dx, again, this is where if you just miraculously drop the dx and it's just gone, or dx just becomes du without any substituting, now you've got these extra x's, and this cannot work. That is never acceptable to have those x's left behind. There are a few substitution tricks that come up, but almost always that will cancel through the derivative work. And now even when I do plug that in here, this one is a little bit more complicated because I can't just selectively pick and choose. I can't just say, oh, sure, x cancels with x, and then 4 plus 4 is 8, and 2 plus 2 is 4. That's nonsense, everybody. It needs to cancel algebraically. So in this type of a situation, yes, x squared divided by x squared, that's a clean cancel. But here, you'd have to cancel the entire factor. So some people, just clever, if you pull a 2 out of this, then everything matches and you cancel. Other people, a little more literal, factor everything. Well, here a 4 comes out and you're left with x plus 1. Here a 2 comes out and you're left with x plus 1. But either way, the x plus 1s cancel, and now we're in a good spot. And now, finally in this one, we're not just left with this extra 2 in the denominator, we're left with a 4 over 2, so that's a clean 2. 2 over 1, but now I've got a 1 over u cubed du, and here's the second issue with this problem. I don't think this problem is that terrible, but I'm trying to use it for two purposes. Number one, that our u's might be just a little bigger than what we were seeing in the previous, so that our derivatives might have a couple of pieces, not just one, and seeing how to simplify those situations. But the second, just because we made a u substitution, everything's not perfect. Technically, when you look at this, well, we simplified the inner-outer, but technically there's still a very minor issue with division here. But that last little issue of division, we can handle that on our own, everybody. That's just a simple variable in a denominator. And again, the 2 out in front, the 2 inside, that doesn't matter. It's about the variable. That is the little extra necessary move. And now, we're right where we need to be. So I simplified with my u substitution, but it's still not perfect. Still just a little manipulating by hand. Now I've got a nice u to the n. The 2 still pushing along. Add 1 to the exponent. Divide by that new exponent. Plus c. And now just nice coincidence, those cancel. Do you leave this minus u to the negative 2? Do you make it a minus 1 over u squared? You know, all that's just little simplifying. That doesn't matter. The big thing that this has left, here or here, is to back sub for u. So in this form, I would be getting minus 1 over x squared plus 2x plus 5 squared plus c. That would be my final answer. Any of these, just like all the other antiderivatives, if you're just getting an antiderivative, I don't mind if you don't simplify, but certainly recognize that the book does like to simplify. So the book, if you finished here and you've got the x squared plus 2x plus 5 to the negative 2, and you still have this, but then you just notice the book has their answer like that, you should be able to realize, they just canceled the 2's and moved that to the denominator, and that you were correct. Okay, so 2 more, everybody. Let's start off with number 4. And for number 4, let's look at the integral. Let's do 8x cubed secant squared x to the 4th minus 6 dx. And now this is looking a little bit uglier. Still uglier still. Multiplication problems. We've got inner-outer, but technically you could talk about layers of inner-outer. This is inside the secant function, but the secant function is being squared. So it feels like there's a lot of layers, but now it's a matter of, and we don't get a lot of this right here, but it almost feels like we have some choices for you. So how do you know what the right choice is? Well, it's the choice where good things happen, meaning things cancel, and secondly, that we get something on our list. So now I'm already going to make a big jump. I'm going to realize that even though I see secant squared is a good thing. U, if I can make the inner part of the secant squared u, then I've got a good clean antiderivative. So I'm just thinking a little bit ahead here, but that's how I'm going to know that this should be my u. If you pick u as secant squared, du, well, I mean, if you just pick u as secant, I'm sorry, then du would be secant tangent, and you still have a lot of x's and nothing cancels. So that's kind of a sign that as long as you know you should make a u substitution, that you just picked the wrong function, the wrong piece for u. So this will work. And again, I'm already looking ahead. The derivative here will give me an x cubed, and that's going to get rid of this extra x cubed. So not trying to push you too far ahead, but just realizing little things like that can really help to keep us on track. Not just at the very end, can we check our answer and see that we did everything right. Along the way, getting these little good feelings that things look like they're working. So yep, that's what I picked as my u, du. I get a 4x cubed dx. I'm already seeing that that's going to help me cancel with that. But formally, again, this is where the book, they'd go, oh, look, break this up. 8 is 2 times 4, and there's your 4x cubed dx. Or just swing the x cubed and do a 4 here and a 1/4 here to keep everything balanced. But I still always say, I think for a lot of students, solving for dx here gives you a cleaner substitution here. So that for the moment, again, keep your notation. All I'm doing is substituting. I'm not taking the antiderivative here. And for the moment, this is hanging out, but this has become secant squared of u. The dx has become the du over 4x cubed. And if I wasn't seeing it here, I see it here. That should be a good feeling that we're on the right track. The x's have canceled. A little bit more, 8 over 4, well, that's 2. But that should be a very good feeling. That seeing not just some x's simplifying, but all of them being gone. And now that still may look a little complicated, but again, it's right on our chart. And not only the secant squared, I've got the du there as well. So the anti of secant squared du takes me to the left, and my answer is, well, don't forget the 2 is still there. Tan u plus c, and back subbing 2 tan of x to the 4th minus 6 plus c. Okay. Last problem, everyone. And I've been picking on the trig functions a little bit. The trig functions, just like we saw for derivatives, just a little bit more. Chain rule comes up. The derivatives themselves are a little bit uglier. So with antiderivatives, the trig functions can be a little bit of a pain. That's why I remember always said just a little bit of trig to get through and just a little bit more to get an A. And a lot of that is getting those derivatives, antiderivatives clear. But for this last one, let's get away from that for a moment. I could definitely do this using a trig function, but I want to do one definite integral and show you something that happens. So let's keep this one fairly easy. Let's look at the square root of 9 minus x, and we're going to go from x equals 0 to x equals 5. So nothing too fancy here. I mean, you want to rewrite this as 9 minus x to the 1/2. That's fine, but nothing really is changing here. And this is one of the more basic inner-outer situations. So I let u be the inner. Du is negative 1 dx. Divide that over. So I've got my integral. I'm not going to write my bounds. I want to see that everything gets plugged in first, that it's working. This is u to the 1/2. That looks good. Du divided by negative 1, so no issue, no extra x's here. And I'm going to talk about pushing the limits. So perfectly fine, antiderivative, the minus 1, a minus 1 in the denominator, a minus 1 out in front, all the same. U to the 3/2 divided by 3/2. Then back sub to 9 minus x and use the x's of 0 and 5. Of course, that's still legit. But this little idea I want to point out specifically goes with pushing the limits. Because if you start pushing the limits here, look what happens. So this is negative u to the 1/2 du. Nothing new here. I'm seeing that this works, so I'm going to push my limits from x is 0 and x is 5 to new u values. And I'll do that using my u substitution, whatever equation I used to substitute u. So if x is 0, u is 9 minus 0, u is 9. If x is 5, u is 9 minus 5, I get 4. Do you notice now I'm out of order? That's something we talked about a while back when we talked about the properties of definite integrals. It was section 4.2. We talked about that if we are setting an integral, of course we'll put our bounds in order from left to right goes bottom to top. But this is just one example. We saw through the definite integral functions that sometimes our bounds could be out of order that way. If I'm going from 1 to x, but if x is 0, then I'm out of order. But this little technique also sometimes puts us out of order. So this would be a situation. You can keep going. You don't have to put these back in order, but especially when I already have that extra negative. This is a perfect spot to get the extra negative and put those bounds in order and to get rid of that negative. I'm not even going to finish the problem, everybody. I just wanted to point that out, that through u substitution and pushing the limits, that could be a situation that our bounds are out of order. When I push the limits, I don't automatically push the lower number to the bottom and the bigger to the top. It was all when I used the bottom x, that gave me the bottom u, and when I used the top x value, that gave me the top u. So that could be a reason that they get out of order and a reason to use that little extra negative to put them back into order. So like I said, no problem at all, everybody. If you want to finish this and compare, finishing antiderivative, get yourself back to the original x's and plug them in. Do it directly here, antiderivative, and plug these in the way they stand, or getting the extra negative, antiderivative, and plugging these in top minus bottom. All three would give you the same answer.